Alright, mastering SolidWorks, Chapter 8, selecting secondary features. When you need to create features that are somewhat outside mainstream, you need to reach deeper into SolidWorks. SolidWorks has a lot of functionality that lies out of the public eye that may be just what you're looking for in certain situations. You probably will not use tools you find in this chapter every day, but knowing about them, they mean the difference between having the capability and not having it. In this chapter, you will learn to define, create curves in SolidWorks, choose occasional special features. Creating curves and features. Curves in SolidWorks are often used to help define sweep and lofts as well as the other features. Curves differ from the sketch of the curves of the defined user sketches or dialog box, and you cannot manipulate them directly to dimension them in the same way that you can sketch it. Functions that are accustomed to using sketches often do not work on curves. The curve features are covered in this chapter are project curve, helix, and spiral, curve through X and Y, Z points, curve through reference point, composite curve, imported curve. Several features that carry the curve name actually sketch base features are 3D sketch, equation driven curve, intersection curve, and face curve. Split lines is another feature that can create edges on the faces that can use like a curve feature. Split lines can function as a curve in some situations. This section discusses split line along with the rest of the curve, other curve like features. Of these, projected helical curves are far most frequently used, but others may be important from time to time. Curve functions do not receive much attention from SolidWorks updates. The curve features are few. In some cases, the functions are buggy. The usefulness of curved features is limited in software, but in some cases there is no other good way to achieve the same results. Tips: when you come across a function that does not work using curve etny, but it works on a sketch, for example, making a tangent spline, it may be helpful to use the curve etny and convert etny's function. Converting a helix to 3D sketch creates a spline that lies directly on the top of the helix and enables you to make another spline that is tangent to the new spline. You can find all the curve function and curves toolbar by choosing insert curve from the menu. Curve features in general have several limitations. Some of these are serious. You often have to be prepared with working around techniques when using them. Manipulating curves. Curves cannot be mirrored, moved, patterned, manipulated in any ways. A workaround from this may be to the convert etny to create the sketch from a curve, or to create a surface using a curve pattern and mirror surface using edge of surface in the place of the curved feature. Alright, you see the little loft symbol on the left. Working with the helix curve feature. The helix curve types are created with a sketch circle. Circle represents the starting plane center with the diameter of a helix. Figure 8.1 show the property manager constant pitch, variable pitch, helical types. Create all helical curve types, specifying some combination of total height, pitch, the number of revolutions. Starts or angles depends on the relation of the sketch plane to the origin. Start angle can be controlled outside of the property manager through dimensioning, design table equations, and so forth. The term pitch refers to the straight line distance along with the axis of the rings of the helix. Pitch of spiral is different and is described later using taper helix panel. The taper helix panel with the helix property manager enables you to specify the taper angle for the helix with the taper angle that does not affect the pitch. If you need to affect both the taper and the pitch, you can use the variable pitch helix. Figure 8.2 show that the tapered angle relates to the resulting geometry. Using variable pitch helix, you can specify variable pitch helix either for the chart or in callouts as shown in figure 8.3. With the pitch for the diameter or variable the diameter number of the first row cannot be changed, but is driven by the sketch and chart shown in transition between 4 and 4.5 revolutions is where the pitch and diameter both change. Figure 8.1 shows helical spiral property manager, giving the helical spiral symbol in the left hand corner, close and checkmark and close, define pitch and revolution, parameters, constant, variable pitch, reverse direction revolution, start angle counterclockwise or clockwise, tapered angle and tapered outward, taper helical panel, taper helical panel degree, tapered outward, variable pitch in helix, helical spiral 1, define pitch revolution, constant, variable pitch, regional parameters, parameter revision, height, diameter, reverse direction, start angle, counterclockwise, clockwise. When double-clicking a helix feature, SolidWorks display with a dimension on the screen, which you can click, then double-click and change with the dimensions displayed in the way that aren't organized when using the property manager, but may be more convenient. Establishing a workflow. One workflow for all helical type curves is followed with draw a circle, select an existing circle, start with the helix command, set the options, click with the green check marked in to accept the feature. Using a spiral, spiral is flattened planing or tapered helix. The pitch value of the spiral is radial distance between revolutions of the curve. See figure 8.4. So now you have a spiral option defined by spiral parameters, reverse direction, revolution, starting angle, counterclockwise, creating projected curve. There are two types of projected curve: sketch on face and sketch on sketch. These names are misleading if you do not already know what they mean. In both cases, the word sketch is a noun, not a verb. You know that actively sketching on surface instead of you're creating a curve, projecting a sketch onto a face. Using sketch on face is option with the projected curve, creating the project 2D sketch onto the face. The sketch is projected normal perpendicular with the sketch plane. The sketch can open. It can be an open loop or closed loop, but is not multiple open. But may not be multiple open closed loop, nor can it be self-intersecting. Figure 8.5 shows an example of projecting a sketch on the face with a created project curve. Projected curve using a sketch on faces option. Shows projected curve, projection type sketch on face, sketch on sketch, face, and sketch. Reverse projection. Using sketch on sketch. Easiest method visualizing sketch on sketch projected curve with the intersecting surfaces method of the even curve created with the intersecting two surfaces with the created by extruding each of the sketches. Then the Stone's method is shown in figure 8.6. Using intersecting surfaces visualize a sketch on sketch projected curve. So show the projected curve sketch profiles. Using curve of the XYZ point features. The curve through the XYZ points features enables you to either type or import text file coordinate from points of the curve. The text file generated with any of the program makes list of the number, including XL. Curve reacts like a default spline. Teeter-tottering effect may be noticeable, especially because you cannot set end conditions with it, or tendency to avoid the fact that it may be a good idea to overbuild the curve by a few points on the other end, or to have a higher density of points. If you import text to the file, have an extension of text or a solid CRV curve that sample data, chapter 8 curve file, solid curve, download material, then the data that contains the most formatted 3 columns XYZ coordinates, you the document with the units in inches, millimeters, and so on. Coordinates must be separated either by a comma, space, or tab. Figure 8.7 shows both curve file dialog box displaying a tab of the table of a curve from the X and Y Z point, solid curve extension notepad. You can read the file from the curve file dialog box by clicking on the browse button, but if you manually type the points in, then you can also save the data out directly from the dialog box. Just like any type of sketch, the type of the curve cannot intersect itself. Figure 8.7 shows the curve file dialog box showing the table XYZ formats, notepad, text file, same information. Using curve through reference points, the curve and show the curve through reference points feature creates the curve at any selected sketch point with the vertices. The curve can be an open or closed loop. The closed loop requires you to select at least 3 points. You can select a condition with the curve. The feature works like a default spline, same way X and Y Z curve. Most common application of this feature is to create a wire with the selected points along with the wire path. Another common application, simple 2-point curve to close the opening of the surface feature with a filled boundary or loft. On the drawback, in regard to the end of the tendency direction, cannot be controlled on the curve features. If 3D sketch spline is used, any end tangent's direction is controlled easily through the use of spline handles and tendencies to construct geometry. Curve through reference points are largely unused, probably because 3D sketch splines are so much more powerful. Putting together a composite curve shows the like a drawing a squiggly line. Composite curves are multiple curves, edge of sketch with a single curve at any spring. The spring shown in figure 8.8 was created by using a composite curve in 3D to join 3D sketch variable pitch helix projected curve. You can also use the model edges composite curve. The curve is shown on half of the part. Result of the part is mirrored. Curves cannot be mirrored, but solid surface geometry can. Composite curves overlap functionality selection manager in some extent. In some ways, the composite curve is nicer because you can save the selection in case of the creation of the feature that uses selection manager fails. If you can create the feature, you cannot save it. Save the selection. On the other hand, composite curves don't function the same way as selection of the model edges and setting of the tangent and curvature. Also, we've the part created from a composite curve. Using split lines, it shows the split line through the middle of a helix. Split lines are not exactly curved, they are just edges split face with multiple faces. Split lines are usually several purposes. They are primarily intended to split faces so that the draft can be added. They are also for creating a broken out face. for a color break and create an edge for the hold-on fillet is discussed in Chapter 7 of the modeling the primary features. There are some limitations using split lines. They must split a face into at least two fully enclosed areas. You cannot have a split line open loop sketch where the ends of the loop are on the face that is to be split. They may be either hang off the face to be split or be coincidental with the edges. If you think you need a split line from an open loop, try using a projected curve instead. Caution: work conditions needed using split lines, especially if the plan is to remove split lines from existing models. Split lines should go as far down as the tree as possible. Split lines change the face of the IDs, of the face of they also split often the edges as well. If you roll back and apply a split line before existing features, you may have a significant number of feature reference to fix. Similarly, remove the split line that has already several dependent features. Many other features may also delete the deleted symbol, lose their reference. Alright, the X and Y Z coordinate with a right triangle, right angle marker with a vision sign. Use an equation-driven curve. Equation-driven curve is not really a curvature feature sketch. It's a sketch technique specifies the spline inside of the 2D sketch actual equation. Even though the spline based on the sketch technique can be controlled only through the equation by using spline control feature is covered in more detail Chapter 3, working with sketch reference geometry while other sketch techniques. Selecting specialty features. SolidWorks contains several specialty features that perform tasks that you will use less often than some of the standard features mentioned in Chapter 7. Modeling primary features. Although you will not use these features frequently as others, you should still be aware of them and what they do, and you never know when you will need them. These features include scale, dome, wrap, flex, deform, and indent. Other types of the commonly used features are specialty categories: sheet metal, multi-bodies, surfacing, plastic, molding, design. These include features such as freeform, combined cavity scale, and several others. I placed a discussion about these features for the chapter devoted for the specialized topic. These features discussed in this chapter are more general use features. Alright, now you see the little box to a big blue box with an arrow. The scale feature is found in Insert Feature Scale. Mainly used for preparing models, plastic parts of the molded cavity geometry. However, they can be used for any purpose on the solid or surface geometry. Scale does not act as a scaling up dimension individual sketches features. Rather, it scales the entire body of the point and feature manager history at which it is applied. Scale property manager shown in Figure 8-9. Then you show the scale parameters about scale, about centroid, uniforming scale, and then you get to choose your degree. Scale features become available only when the part contains at least one solid surface of the body. You can scale multiple bodies at once, selecting one of the three options: scale, about, setting, and fixed references. Part origin, geometry, centroid, custom coordinate system. On these general, preferably select part origin because you must often want the standard plane move with the rest of the part little as possible. If you need to scale specific point of geometry, you need to create the custom coordinate system at the point using the reference. The scale factor works multiplier. If you want to double the length, you would enter with a scale factor of 2. This does not work like a scale function cavity feature, which is left commonly. Scale of the cavity scale feature shown in percentage increase over the double the linear dimension of a part would be require a scale of 100% of the cavity. Even the feature that be able for the context assembly that has fallen out of favor with the most of the mold design. Scales configure means of the different configuration, even the different scale factor configurations are covered in Chapter 11 of working with the part configurations. Interesting aspect of the scale feature is that you disable uniform scaling options. This allows you to separate scale factors X, Y, and Z coordinates in molding making. This could be either using fiber-filled material. The mold requires differential shrink compensation based on the direction of the plastic flow. Thus, the fiber alignment, the part will shrink less than the direction of the fiber alignment. But it could use the size of generally any part, but just remember that apply to different scale circles may be distorted. To get around this, you may be able to reorder the features to apply a scale feature before circular features are added. Because scales are simply added to the body rather than features in sketches, it can be applied with an imported part as well as SolidWorks native part. Sometimes people use the scale feature to compensate for the improper imported units. For example, this part of the originally built with the inches transmitted into millimeters. You want the scale to be the part with a factor of 25.4. You can enter the expression scale factor for the import. The units end of error went in the other way, but the scale of the part down to 1/25.4. Limitation scale features of the SolidWorks metal spacing single part with the box approximately 500 to 700 meters centered or about the origin. There appears to be some difference between sketching limits and 3D solid limits. Implication scale feature for the not stated outright, but it does not scale feature for the sketch for the dimension, and the history-based feature for the side. The difference only appears after the scale feature is in the tree. Alright, then you have the dome, on the dome picture on the left. The dome features SolidWorks generally apply, but it gives some of the shape of the flat surface area of the flat face. Great example of the dome fit well with a coupled cup bottom of the plastic bottle, slightly arc with the top of the buttons, electronic device. Domes can be added with the remove of the material. Still, SolidWorks 2010, another very similar feature existed, which was called shape. You can no longer make shape features because you may run into one from time to time in old parts. If you find a shape feature on the old part, continue with the function unless any of the parent geometry changes. Shape features do not update in SolidWorks 2010 or later. SolidWorks recommends you recreate geometry any other feature possible with the dome freeform feature included in the sample part of the Chapter 8. And this part is called Chapter 8 Dome Solid Part. This part is shown in Figure 810. Opening the part will allow you to see the error that appears when you open the part with a shape feature of the part. All demonstrate some of the ways in which dome features can be used. Best practice. Dome features are best used when looking at the generic bulge or indentation and not intended to concern all about the controlling specific shape. Occasionally a dome may be exactly what you need, but when you need precise, predictable control over the shape, then you should use the fill, boundary, or loft feature. The dome feature has several attributes that are either helpful in qualifying to give it the task to disqualify it. The attributes can help to decide if you will useful situation you encounter. The dome feature can create multiple domes, multiple selected faces, and single feature, although it creates only a single dome for each face. Using an elliptical dome setting, the dome can be create feature in that is tangent to the vertical. Dome can be constant sketch to limit the shape. Dome works on non-planar faces. Dome cannot establish tangent relations to faces bounding a selected face. Dome cannot span multiple faces. Dome display temporarily untrimmed four-sided patch that extends beyond the selected face when you use non-four-sided face. Dome functions only on a solid, not on surface. Dome features have two notable settings: elliptical dome and continuous dome. Elliptical dome is valid on flat face boundary, either with a complete circle or ellipse. Cross section of the dome elliptical does not account for the draft, which means the away tangent for the perpendicular from the selected flat face. Continuous dome is a setting with a non-circular elliptical face, including polygons, closed loop splines. Setting results single unbroken face. Select continuous dome setting functions. Elliptical dome setting. Figure 810 shows the most useful setting of the dome feature. 810 shows example of various types of domes. You have the dome, opened, parameters, direction, sketch, and arrow. Continuous dome over here on the bottom, continuous dome to the right, non-continuous dome to continuous dome, elliptical dome, non-elliptical domes. The workflow for a dome feature is as follows. Select an area to be domed using the split line to create an area to be domed on an existing line. Initiate the double feature set at the height. Tell it to add or remove material set. The other settings including constraint sketch except for the feature for the green mark, check mark icon. Alright, show for the wrap feature. Wrap feature enables you to wrap 2D sketches around analytical complex faces. Trying to wrap it around 360 degrees can cause some difficulties. You might try the sort of thing on two steps. Either two wraps or combination feature. Wrap feature, flatten face, relating sketch, a flat pattern and face mapping with the face boundary, sketching back a 3D face. It's not a simple projection. It actually does wrap the sketch on the curved faces. Figure 811 shows the wrap property manager interface along wrap onto a cylinder, wrap onto complex shape. Complex wrap is available to download materials for this chapter. Complex wrap solid part. Show the drawing on the side of the cylinder. The wrap part is manager interface. It shows wrap and it shows the different drawings and wrap method. Parameters, sketch faces, dimension, pull direction, accuracy, load it high, preview low accuracy, preview faster, and full preview. Wrap features have three main options: emboss, emboss, and scribe. Wrap can be placed analytical, cylindrical, conical, or the like. Flex lines, places, loft sweep, and etc. Using scribe. Scribe is the simplest option to explain and understand. It can be helpful to understand other options. Scribe creates a split line like an edge of face. Several requirements must meet in order to make a wrap feature work. Face must be a cylindrical, conical face. The loop must be closed loop, nested, closed loop, 2D sketch. Sketch must be on a plane either tangent or parallel to another plane that is tangent to the face. Wrap surrounds wrapping over the multiple faces. Wrap should not be used self-intercepting wraps around the part. Self-intersection will not cause feature to fail, but only on other types of emboss and deboss, or maybe produce unexpected results. Scribes can be created with a solid or surface face for the scribe surface with the frequently thickened to the created with the boss or cut. Figure 8, 12 show the scribed wrap using embosses. Wrap and emboss option works like most like scribes, but adds material inside closed loop. Sketch for the thickness specified by the emboss property manager. Embossing can be done only in solid geometry, and the feature itself of the intersecting area is simply not embossed and is left at a level of the original face. One result is creating a fully wrapped around feature. This geometry with a barrel cam requires the second feature for the cover the wrap features away. Always a gap regardless of whether the sketch is to be wrapped is under and over diameter multiplied by pi length. When using emboss option, you can set up the direction of the pull, assign the drafts over the feature injected molded. This limits the side of the emboss so that it must not wrap more than 180 degrees around the part. Alright, using deboss. Deboss is just like emboss, except that it removes the material instead of adding it. Figure 812 to demonstrate that all these option parts shown in the image available to download material under file name Chapter 8 wrap solid part. For each demonstrated case, the original flat sketch is shown and given some an idea how the sketch relates to the finished geometry. So the wrap feature of the option show the scribe etched on the sketch on the side. It's closed loop profile sketch. Solid strip of the feature thickening into solid pattern. Emboss barrel. Closed loop profile sketch. Emboss barrel cam. Keep in mind, this feature is not like projected sketch. The projected sketch is projected normal, and the sketch plane sketch that is 1 inch long with the flat is measured 1 inch one with the wrapped around with the curvature surface. It will measure less than 1 inch linearly from end to end. The emboss can be employed with the workaround revolve feature to close the gap that is always created with the wrapping all the way away around the part. Example, the deboss text employed with the direction pull draft so that the geometry can be molded. Sample models are available to download material Chapter 8, deboss, emboss, and scribe. Alright, show the flex feature. Flex feature different from the most of the other features of the Solidworks. Most create new geometry, flex or deform, which follows. The existing geometry changes its shape. Flex can affect the entire part of just a portion of it. Flex works on both sides and surface of the bodies, as well as import native geometry shown in Figure 813. Flex 4 main option, many settings. The 4 main options are as follows. Bending the option establishes two trim planes denote the ends of the bent area and specify the angle of radius to be bent. Twisting option establishes 2 trim planes limiting area of the twist. Enters the number of degrees through which to twist. Tapering this option establishes 2 trim planes to limit the area with the taper of the body is larger to one end of the smaller toe of the other. Stretching the option establishes the 2 trim planes to limit the area of the B sketch. Stretch, you can stretch an entire body by moving the trim planes outside of the body. Figure 813 shows the flex feature creating. You have the flex, your split input, bending, twisting, tapering, sketching, hard edges, degree, trim plane, vertex, dimension, degree, XYZ, degrees, and arc, triad, direction, universal coordinate, split, flexing option, small to large. Best practice, flex is not a kind of feature that you should actually design parts, but it can be extremely valuable when you need to flex a part in use of the tape. A simple example would be a rubber strap that stretches over something when used, but designed, manufacturing for each state with the geometry that you create by using flex function is not generally production model quality, but usually adequate. It looks like a model. Part shown figure can be found in download material under file name Chapter 8 Flex Solid Part. In some cases, the triad trim planes with a slightly disoriented. The best thing to do in situations simply reorientate the triad using angled numbers for the triad panel with the property manager. This solution of the planes turned in such a way that the axis, depending on the not oriented with the bend of the part required. The flex feature is very conscious and separated by. In some cases, it can be helpful, but in default situation, where there's only one body in the part that can be annoying. Remember to do this. Select the body effect with the very first selection box at the top of the property manager. If you want to bend only one tab onto the grommet. The best solution is split single of the body with a two body flex only on the bodies, and splitting a single body with the multiple bodies and covered in chapter 31, modeling multi-bodies example showing twisting, sketching using technique. You can place the trim in the planes by selecting model vertex, dragging the arrow over the plane, and typing in a number. And by carefully dragging the plane across arrows, because the dragging of the border of the plane drag over the flex value of the feature, dragging the plane and bending the operation like changing the angle and the radius of the bend for the bend. Using a triad can be very tricky. Moving the triad and bending of the option moves the axis for the bend. Something determines whether the bend compresses or stretches the material. The position of the triad determines the side of the bent body move the stationary. If the both sides move, placing the triad directly on the trim plane can cause the material outside of the bend on that side of the trim plane to remain stationary. I highly recommend looking in the models provided within this chapter to examine the various functions of flex feature more carefully. The model use configuration which are covered in chapter 11, working with part configurations. Alright, applying a deform feature. Like a flex feature, deform feature changes the shape of the tire model without regard to parametric feature history dimension. Some software patches call this technique global shape modeling. Also, flex deform works on surface models as well as solids. Deform can also handle imported geometry as well as Solidworks native parts. Model complexity is not as an issue unless the part runs itself with deformation. Deformation features another feature type that may not be actually designed to anything, but you may use to show the model in deformed state. Best practice. Typically, if you want the model to have certain shape, you need to intentionally and precisely model it with that shape. The problem is with the deformed flex geometry, actual design, and the data that both create fairly approximate geometry process yield as a result not completely intentional. The shape of the finally achieved the result of the arbitrary uncontrolled function of the feature, not necessarily changing the shape that had clearly envisioned beforehand. Deform has three types. Point, the type that deforms the portion of the model by pushing a point in the geometry around it. Curve to curve, the most precise in use of the deform type of the type selecting existing edge and forcing the edge to match a curve. Surface push, the type of deform, consequently very interesting function, nearly unstable. The practice of the part, deformed shape vaguely resembling an intermediate shape between existing state of the part and the tool body. Figure 8.14 shows the property manager interface, deform feature interface. Different. Each of the three main types change depending on selection within the individual types interface shown as for the curve-to-curve types, because I believe this is to be the most useful type. 8.14 shows using a deformed shape to the chair back. Deform type point, curve-to-curve surface push, pointer face, direction, deformation height show. Region, deformation, shaded region, shaded axle, and then level on the plane of shape. Looking at point deform option enables you to push a point on the model. Model deforms as if it were rubber. Key to you for the feature ensure the deform region option is unselected. Aside from that, you just have the trial and error when applying the point deform option. The depth and diameter shape of the deformation is not very precise. Also, you cannot specify the precise location of the point to deform. Again, with the best sheet that looks like model, not production data. Looking at a curve-to-curve deform, before the curve-to-curve deform is you the curve that's sketched with the edge data, the most precise method than other deform types. Main concept that is here is to transform a curve on an original model to a new curve, thereby deforming the body of the shape of the new geometry. Model shown in figure 8.15 has created a curve-to-curve deform, and the part steps are a simple sweep, and the arc length and an arc, and then the split line is created with a limit of the deform specified area of the model. The model is downloaded files under file named Chapter 8 Deform Curve-to-Curve Solid Part. Using the curve-to-curve deform, you've down to the deform type curve-to-curve edges and sets, and shown preview, fixed edge uniform, anchor, face, shaded regions, shape option, graded mesh, fixed moving scale, maintain boundary matching note, surface tangent curve of direction. Looking at, and then shows over here, shows initial curves and tangent curves. Looking at surface push deform, I don't go into much detail surface push deform type because it is not one of the more useful functions of SolidWorks. In order to use it, you must have the body of the part that you are modeling tool body that will use the shape. The part you are modeling, the finished shape, does not fit the tool body directly, but looks about halfway between the model and the tool body, blended together in an abstract sort of way. Looks like a dent that would result from an object being thrown very hard in a car fender. In either way, throwing part nor a fender is immediately recognizable from the result. Using the indent feature, indent uses the same ingredient for the surface push, but produces a result that is more useful. For example, by building a plastic housing around a small electric motor for the indent feature shape, the housing creates a gap between the housing and the motor. Figure 8.16 shows Property Manager interface indent feature as well as what the indent looks like before and after using the feature. In this case, a small motor is placed when it needs to be with the wall and with the wall in the way. Indent is used to create indentation in the wall by using the same wall thickness, placing a gap of tenth of an inch, or hundredth of an inch around the motor. Motor is brought into a wall part by inserting part command. The multi-body technique. Multi-bodies are examined in Chapter 31, Modeling Multi-Bodies. Using indent feature, we've now picked the indent. We've targeted the body, keeping selections, remove selection, total body region, cut, dimension, and direction. So here is the picture. We've now moved the indentation into there, and it's moved around. So we've indented this part into a surface. It is possible to indent molded application. However, the most mold designs will prefer the use of the shrink percentage. You can get that with scale cavity bowling operations rather than discrete offset indent provides. Using intersect combines functional general solid bowling operation, trim surface split, replace face cut with surface. Tools does not appear to have the exclusive functionality. Reduce work to complete the sum of the tasks that usually take many steps with a combination of different tools. It's useful to determine the volume open cavities. For example, the part file shown Figure 8.17 multiple body solid surfaces. The small part over the center is the knob. The big block around the mold block is currently a single piece. The 4 cylinders are special surface representing a lining pin cylinder in the center is an ejector sleeve. At the top of the plane goes through the center representative of the part of the line of the mold. You can find this part in the downloaded material Chapter 8 under the file name Chapter 8 intersecting example solid part. Figure 8.17 creating a mold representing solid surface with the intersecting starting point and inch of the tree, surface extrudes. First step to select the entities involved as much of the mutual trim feature selection panel with the intersecting property manager. Select every solid surface in plane that will take part of the operation. You have the option to cap open surfaces with it does while doing this, but the example does not require it if one of the holes is a blinding hole, but the surface body will open inside with a solid. The situation will require the cap surfaces. In the example, the one thing with the feature that is not very elegant with the merged result is not selected. Perhaps you can think of the best splitting function that is not selected with the notice of the fillet feature that is tree combined. This is necessary because of the original part was split into pieces. You may argue the original part should be consumed, in which some case they would have allowed the piece to remain. But this kind of decision should be up to the individual user, not the programmer. Consume surfaces option simply remove any surface body used in the operation. Tutorial, creating a wire-form part. The following these steps of the created wire-form part. Open the new part with the in-space template. Open the sketch to the right or on the right or side plane. Sketch a circle in the center of the origin diameter of 1/2 inches. Create a helical constant revolution pitch of the 1/4 inch. Revolutions at 5 1/15 of an inch. Start angle 0. Helical command is found in the insert curve helical in a spiral. Creating a sketch in front of the plane shown in Figure 8.18. Pay careful attention when adding construction line shown line using next sketch step to reference the end of the arc. So result step 4, here's the helical. It shows the radius of and 1 inch is 1/4 inch and 1/2 inch, 1 3/25 open. Open the sketch right plane. Use the information in Figure 8.19. Add the correct relation direction. Be aware the 2 sketches shown with a different sketch plane make it difficult to depict 2D. You can also open the part from the download materials and reference. Sketch 5, step 5, coincident vertical relation. Dimension reference construction line. Exit the sketch and create a projected curve. The projected curve function is found with the insert curve of the projected curve sketch on the sketch option. Open 3D sketch. You can access 3D sketch from the insert menu. Select the helix. Click convert etnies sketch toolbar. Select with the projected curve. Click the convert etnies again. Now 2 sections 3D sketch that are not connected in space. Draw 2 points spline joint ends of the 3D sketch and enter the closest to one to another. Assign the tangent relation. The ends of the make the transition smooth. Figure 820 illustrates what model should look like at this point. Result of step 8, connecting spline, adjusting length of this handle. Tip, you may have to adjust the length of one of the spline tangent length arrows to keep the spline from remaining inside the cylinder or helix. Open the sketch with the right plane, draw over the arc with the center of the origin with the coincident with the end of the 3D sketch heel with a 185 degree angle to create with the activated with the dimension tool. Clicking the first center of the arc, then to be 2 endpoints of the arc. Now play the dimension type of the dimension allows you to get the angle of the dimension to the angle blinds. Exit the sketch. Create a composite curve, insert curve, composite existing 3D sketch with a new 2D sketch. Create the next plane with a normal curve option, selecting one end of the composite curve. On the next new plane, draw a circle with the center of the end of the curve with the diameter of the 1200ths of an inch. You need to create the Pierce relation between the center of the circle and the composite curve. Create the sweep feature view of the circle with the profile of the composite curve as the path. To create the sweep, you must first exit the sketch. Hide any of the curves is still displayed. Choose insert cut with the surface flyout and feature manager. Select the right plane. Make sure the arrow is pointing side of the plane with the least amount of the material. Click OK to accept the cut. Finished part is shown figure 821. Finished part, and it's got bottom line. SolidWorks has wide range of features beyond basic extruded revolves. You see with the depth of the standard feature chapter 7, the modeling of the primary features now in chapter 8. You see in the breadth of some of the less used but still useful operations. You want to use each of the secondary feature every day, but it's nice to know that you need to show the model in a flex in use state. That at least you at least don't have to already directly model the deformed part manually. The needed custom design spring is design small mechanism and quite common. Having the ability to create such designs valuable is skill. Master it using helical 3D sketch to create a sweep path with a spring elongated the ends of the light mechanism. Packaging fixture additional types of design modeling and import for and engineering master. Create cavity such as the file name in chapter 8 biosolid part and can nest it into it. Master it. Use the indent feature to create cavity in a thin sheet of material. Text often to go any regular shift with working on examples to gain some experience putting in there. Master it. Download chapter 8 total tutorial bracket castings solid parts. Some of the text is wrapped into one cylindrical boss. This is part of the model number of the second boss using same process. Chapter 9 patterning and mirroring.